Hi guys, today we will tackle about the structures of an atom. We're here together with our group mates. My name is Harold.
I'm Milen.
I am Nico.
I'm Yoan. Hi, I am Princess.
Hi guys, and I'm Olsen. Dear guys, who do you think discovered the atom?
Who discovered the atom? The idea that matter is made up of infinitely small, absolutely simple, indivisible pieces is hardly new. The Greek thinkers Leucippus and Democritus suggested the idea a good 100 years before Aristotle declared it was nonsense. However, the idea has only carried scientifically for the past 200 years. It already took off in the past century.
Dear guys, what are the three main parts of an atom?
The three main parts of an atom is proton, electron, and neutron. So first, what is a proton? Proton is a subatomic particle symbol P or P plus with a positive electric charge particle. Second is the neutron. Neutron is an uncharged particle of an atom, and it's like in proton, it is also found within an atomic nucleus. And last, the electrons. Electron is a negatively charged particle located in the shells that can surround the atom nucleus.
We already know that atoms are really small, but we can get smaller. If we zoom into an atom, we find that it is made up of protons, neutrons, and electrons, and a lot of empty space. Imagine an Olympic swimming pool, 50 meters wide. This is our atom. At the center of our atom is the nucleus. The nucleus is made up of protons and neutrons. But if we jumped into the pool to find the nucleus, it would be pretty much impossible, because it is the size of a grain of sand. Around the nucleus, we find that electrons are randomly whizzing around. The electrons are even smaller than protons and neutrons. So say we only have 2 electrons in our atom. These would be randomly moving around our grain of sand in our 50-meter pool, just these 2 tiny electrons. So what does that leave? A lot of empty space. Now if we think about the minuscule scale that we're talking about, the constituents of an atom must have a minuscule scale to match. If we were to weigh protons, we would need 600 sextillion to just weigh 1 gram. So 1 proton would have a very, very small mass, and the same is true for neutrons and electrons. This is why we weigh them in relation to each other. We assign the mass of a proton as 1. The neutron has a similar mass to protons and is also given the mass of 1. The electron, however, is much lighter and has a mass of 1/1840. If we think about how heavy the mass of the protons and neutrons are in relation to the electrons, it's clear to see that the mass of an atom is concentrated at the nucleus. Protons, neutrons, and electrons also have a charge associated with them. Protons are positive, neutrons are neutral, and electrons are negative. The charge of an atom is always neutral. This means there must be the same amount of protons as there are electrons in an atom. The number of neutrons can vary, and they do not affect the charge of the entire atom.
Back to the small, where we begin our climb up the ladder of structure. This is how we represent an electron visually. The particle itself is a fundamental particle and is too small to be seen by any imaginable instrument of observation. So we instead represent the properties that allow the electron to interact. The central small dot represents the weak charge of the electron. This charge, entirely separate from electric charge, gives rise to the weak nuclear force. This force causes radioactive decay, and its typical range is much smaller than the diameter of a proton. The larger volume of shifting purple is meant to represent the electric charge of the electron. This charge is the generator of the electromagnetic force, which has infinite range, although the drop-off of strength is pretty dramatic as we move away from the electron. The electromagnetic force is how electrons interact with other electrically charged particles and with magnetic fields. These interactions make the structure of atoms and molecules possible. This gives rise to almost all of the complexity that we see around us. This is our depiction of a proton. It is composed of 2 up quarks and 1 down quark, as you can see from the tiny rings of color near the center of the quark. The overall charge of the proton is positive, and so we have given it a gold shell. Note that we can simply add the charges of the individual quarks to get the charge of a proton. Oh, protons taste sour, like vinegar and lemonade. This is our depiction of a neutron. It is composed of 2 down quarks and 1 up quark, as you can see from the tiny rings of color near the center of the quark. The overall charge of a neutron is neutral, so we have given it a silver shell. Note that we can simply add the charges of the individual quarks to give the charge of the neutron. The red, green, and blue colors of the quarks represent the color charge which generates the strong nuclear force that holds them together. It comes in 3 different charges, represented here by 3 colors, and for different colors, the force is attractive. The mediator of the strong force, the particle that is exchanged in an interaction, is a gluon. We represent gluon exchange as the occasional wispy string between the quarks. As you can see, the gluons have color themselves, and each gluon exchange causes the quark involved to swap color. Although we show quark motion inside of the neutron as leisurely, they are actually traveling close to the speed of light. There are 2 kinds of quarks that are found in normal matter. Physicists call them flavors of quarks. These quarks are the up quark and the down quark. A proton is formed from 2 up quarks and 1 down quark, while its slightly heavier cousin, the neutron, is formed from 2 down quarks and 1 up quark. The red, green, and blue colors of the quarks represent a property that attracts them to one another. It is this color charge property of the quarks that hold them together in a proton or a neutron. These protons and neutrons can then combine to form the nucleus of each element in the periodic table. 1 proton in the nucleus makes hydrogen. Two form helium. 6 carbon. 8 oxygen. 79 is gold. And 92 uranium. Neutrons help hold the protons together. Because of their electric charge, protons would repel each other more strongly if neutrons were not present, and the heavier elements would come apart. There are approximately as many neutrons in each element as there are protons. Atoms are formed when the positively charged protons in the nucleus capture the negative electrons. Neutral atoms capture 1 negative electron for each positive proton in the nucleus. So, hydrogen has 1 electron to go with its 1 proton. Helium, 2 electrons. Carbon has 6. Oxygen, 8. Gold has 79. And uranium, 92. There are nearly 90 stable elements. The largest of them contain close to 800 fundamental particles, joined in a complex but stable structure. But electrons cannot just gather around in a crowd. Once again, the strange, wonderful world of the tiny has its idiosyncrasies. Electrons arrange themselves in shells inside an atom like the layers of an onion. And only 2 electrons can fit per layer. So the more electrons an atom has, the further away from the nucleus the outer shells must be. And that means these electrons are more loosely held. It is this difference in how tightly electrons are held in each different kind of atom that determines the chemical properties of the element. This accounts for the ability of metals to conduct electricity, the aloofness of noble gases, and the formation of molecules. It turns out that protons in 2 or more different nuclei can sometimes capture and fight over the same electron. And when that happens, atoms of different elements are joined together to form molecules. This oxygen molecule is sharing 2 of its electrons with 2 hydrogen atoms. This is how a water molecule is formed.
Dear guys, what are the 3 models of an atom?
The 3 models of an atom are plum pudding model formulated by J.J. Thomson,
Bohr's model by Niels Bohr, and Rutherford's model formulated by Ernest Rutherford.
Back home to you.
The first major discovery that set off modern atomic theory was that atoms are not, in fact, the smallest things that exist. John Joseph Thomson discovered the electron in 1897, which led him to posit a plum pudding model, aka the Risen pudding model, for the atom. Electrons are small negative charges, and Thomson suggested that these negative charges are distributed about a positive charge, medium like palms in a plum pudding. The negative charge electrons will balance out the positively charged medium so that each atom would be a neutral charge.
The second one is the Bohr's model. The Bohr model shows the atom as a small, positively charged nucleus surrounded by orbiting electrons. A stylized representation of a lithium atom illustrates Niels Bohr's atomic model, that an atom is a small, positively charged nucleus surrounded by orbiting electrons.
And lastly, we have the Rutherford model formulated by Ernest Rutherford. In this model, it represented the atom to be much like our solar system, with the electrons orbiting the positive nucleus like planets orbit the sun, and according to this model, the electrons would have been accelerating as they orbit the nucleus due to the net centripetal force acting on them. This should cause them to emit electromagnetic radiation, and they should then lose energy, causing them to collide into the nucleus and implode the atom. However, since this does not occur, this model failed as well.
Atoms are ridiculous and unbelievably small. A single human hair is about as thick as 500,000 carbon atoms stacked over each other. Look at your fist. It contains trillions and trillions of atoms. If one atom in it were about as big as a marble, how big would your fist be? Well, about the size of Earth. Still hard to imagine? Let's try something different. Look at your little finger. Imagine that its tip is as big as the room you're sitting in right now. Now, fill the room with grains of rice. One rice corn represents one cell of your fingertip. Now let's zoom in on the rice corn. And now one cell is as big as the room you're in right now. Let's fill it with rice again. This is about the size of a protein. And now let us fill all the empty spaces between the rice corns with fine grains of sand. This is roughly how small atoms are. What is an atom made of? Let us just pretend that atoms look like this for a minute to make it easier to understand. An atom consists of three elementary particles: neutrons, protons, and electrons. Protons and neutrons bind together and form the atom core, held together by the strong interaction, one of the four fundamental forces in the universe. They are made from quarks and held together by gluons. Nobody knows exactly how small quarks are. We think they might literally be points, like in geometry. Try to imagine them as being zero-dimensional. We suspect that quarks and electrons are the most fundamental components of matter in the universe. Electrons orbit the atom core. They travel at a speed of about 2,200 kilometers per second, fast enough to get around the Earth in just over 18 seconds. Like quarks, we think electrons are fundamental particles. 99.99999999999% of an atom's volume is just empty space, except that it isn't. What we perceive as emptiness is actually a space filled by quantum fluctuations, fields that have potential energy and build and dissolve spontaneously. These fluctuations have a fundamental impact on how charged particles interact, but that's a topic for another video. How much space do the core and electrons actually fill? If you were to subtract all the spaces between the atom cores from the Empire State Building, it would be about as big as a rice corn. All the atoms of humanity would fit in a teaspoon. There are extreme objects where states like this actually exist. In a neutron star, atom cores are compacted so densely that the mass of 3 suns fits into an object only a few kilometers wide. By the way, what do atoms look like? Well, kind of like this. Electrons are like a wave function and a particle at the same time. We can calculate where an electron might be at any given moment in time. These clouds of probability, called orbitals, are where electrons might be with a certainty of 95%. The probability of finding an electron approaches zero the further we get away from the atom core. But it actually never is zero, which means that, in theory, the electron of an atom could be on the other side of the universe. Okay, wait a second. These strange thingies make up all the matter in the universe. For many dozens of known elements, you don't need many dozens of elementary particles, just 3. Take 1 proton and 1 electron, and you have hydrogen. Add a proton and a neutron, you have helium. Add a few more, you get carbon. A few more, fluorine, even more, gold. And so on. And every atom of an element is the same. All hydrogen atoms in the universe, for example, are the same. The hydrogen in your body is exactly the same as the hydrogen in the sun. Do you feel confused right now? We certainly do. Nothing on this scale of the universe makes any sense in our world, and we've not even begun talking about quantum mechanics or the particle zoo, which are even stranger. Our model of atoms has changed a number of times since we first conceived it, and the current one will certainly not be the last. So let us support scientists and research and wait for the next wave of mind-boggling new information about this strange world that is the basis for our existence.
That's all, guys!
Thank you for watching us.
And I hope you learned something from us.
And if you want to watch more videos, visit us on www.olsenmaydor.com.ph.
And you can follow us on Twitter at Olsens.
But you can follow us on Instagram at Olsen.
And subscribe.
Peace! Woo!
Girls, what y'all trying to do? 24 karat magic in the air.
Ulit, di ko alam sabihin kayo. Dear guys, who do you think discovered the atom?
Who discovered the atom? The idea that matter is made up of indefinitely. Ang hirap kasi kapag
Hindi kita sila. Yan. 1, 2, 3, go. I hope...
That's all, guys!
Thank you for watching us.
I hope you learned something from us.
And if you want to watch more videos, visit us on www.olsenradar.com.ph.
And you can follow us on Twitter at Olsens.
And subscribe, but it's... Dear guys, what are the three models of an atom?
The three models of an atom are plum folding model. Ba't may tumawag? Plum folding.
The other
Ulit, di ko alam sabihin kayo. Ulit, di ko alam sabihin kayo. Ulit, di ko alam sabihin kayo.